today, and as a motivation for our study, I want to point out that there is a lot of hybridization observed in nature, and sometimes it goes on for a long time. And this, together with the observation that sometimes speciation is completed, leads to the question, how does reproductive isolation become complete, and why does it sometimes be completed and sometimes not? And so out of the mechanisms that could complete speciation, the one that we have been studying is reinforcement. And so we're asking what the role of reinforcement is in completing a speciation process. And I think I don't need to explain what reinforcement is anymore, and so I can go, descend to the questions of our study. And so we are asking how strong reinforcement is in a population that is on the verge of speciation, so that is already has already diverged and is very close to complete speciation. And we're in particular we're asking how different the strength of reinforcement is as a result of one or two allele mechanisms. And if we translate this into modeling language, this means that we're asking for the selection coefficient or the invasion rate of a modifier, and in our case of a female preference in a diverging population. And so now I will introduce the model, and so we have tried to make the most simple model possible, and so we're dealing with a haploid model, and for a haploid model to get like 3 phenotypes so for reinforcement to work we need disruptive selection on intermediate phenotypes, and so for our haploid model we use 2 ecological loci which determine a male trait that is under disruptive selection. So we have 3 different phenotypes produced by 2 loci, and the intermediate phenotype suffers from disruptive viability selection, and this is only on the male, working on the male trait. And then we have a female preference locus that determines the preference for a certain male phenotype. So here are 2 different female preference alleles. One kind of female has a preference for blue males and the other one for green males. And as a 4th locus we introduce the modifier, and the modifier changes the strength of this female preference. And we are making a very, so the life cycle then is as follows. So we have viability selection on zygotes, then mating according to the female preference, and afterwards free recombination between all loci. And we are also making a very important simplifying assumption. So we just assume that there is some kind of frequency-dependent selection that is keeping the preference and the trait in equilibrium of allele frequencies 1/2. And next I will introduce the model parameters. So first we need a parameter for the strength of the existing female preference, which I call phi, and phi is 1 over a female preference value PE. Then we can construct arbitrary preference functions determined by a parameter P capital I, which include both the effects of viability selection and sexual selection. So we can construct preference functions with only viability selection, only sexual selection, and combinations of both. And last we have the effect of the modifier on the extreme phenotypes delta E, and the effect of the modifier on intermediate phenotypes delta I. And I think everybody knows by now what a 1 or a 2 allele mechanism is, but I will give an example of how these work in our model. So for example here you see an example for where we have the strength of the preference to be 10. So the existing preference is 10, and blue-liking females will prefer to mate with blue males, and they will mate with them 10 times more likely than with green ones. And because of our symmetry assumptions, it's exactly the other way around for females who like green males. And then in the 1 allele mechanism, females who carry the modifier, they will generally have a stronger preference for the kind of males they liked before. So here, for example, if we have a modifier of strength 0.5, blue-liking females will have a twice as high preference for blue males, and green-liking females will have a twice as high preference for green males. And in the two-allele mechanism, in contrast, the same thing. So this is similar for the thing is similar for green-liking females. They also have a stronger preference for green males, but this only, like, the modifier only strengthens the preference in combination with a green preferring allele of females. But if it's occurring in a female which originally liked blue males, then she will also have a new induced preference for green males, and so in the end this will reduce her existing preference for the blue males. And so back to the main questions, we are asking in which conditions such a modifier will spread in the population and what the rate of invasion is. And so as a method, we're using the multi-locus model framework, which was developed by Martin and Turelli and elaborated by Kirkpatrick et al. And so it enables us to derive exact recursions for the associations, which are kind of higher order linkage disequilibria between loci. And then we are doing a quasi-linkage disequilibrium approximation and quasi-linkage equilibrium approximations to find simple expressions that describe the rate of spread of the modifier. And yeah, so this quasi-linkage disequilibrium means that we use a state as initial an initial value for the invasion of the modifier that is close to speciation, so close to full linkage disequilibrium in the population. And so our first result is the quasi-linkage disequilibrium approximation for strong preferences, and so we get an analytical result which is dependent on the preference value for extreme phenotypes and the shape of the preference function. And visualize this looks like this here. So on the x-axis is the strength of the preference, and on the y-axis is the amount of linkage disequilibrium between the preference and trait alleles, and here between the two trait alleles. And so yeah, the triangles and dots are numerical results, exact results for different preference functions, and the curves correspond to our approximation. And yeah, so what you can see is that with growing preference, we converge to full linkage disequilibrium, and so of course 0.25 would correspond to full speciation here. And so these are the values we use as initial values for the invasion of the modifier here. And then, yeah, we get some really nasty equations, and we really need approximations to make to derive any results from this, but fortunately it really works, and we get analytical expressions for both the one allele mechanism and the two allele mechanism. And maybe I will first show a graph of this. So here on the x-axis is but on the x-axis is the amount of linkage disequilibrium between the trait alleles, and so this goes like here from 0.15 to 0.25, which corresponds to completed speciation. And I've also written down here the percentage of intermediate offspring which are still in the population if we have an existing preference that produces this amount of linkage disequilibrium. And then on the y-axis, on a log scale, you see the invasion rate of the modifier here, which I call lambda, and the dots are the numerical exact results for in blue a one allele mechanism and in gray a two allele mechanism, and the curves correspond to the approximations here, and this is for a modifier of small effect, so here the effect is 10%. And yeah, there are several things you can see from this. So first is that if we are close to complete speciation, the approximations hold really well. And yeah, but on the other hand, the closer we get to speciation, the more quickly the strength of reinforcement, which is measured by this invasion rate here, decreases, and we also see what we had expected before, that this is even more, this happens even quicker for a 2 allele mechanism than for a 1 allele mechanism. And now if we really want to quantify the strength of reinforcement, we can, for example, interpret the invasion rate as the selection coefficient of this modifier allele, and maybe compare it to the probability of a neutral allele to become fixed in the population. And so this dashed line here, for example, corresponds to an invasion rate of 10 to the minus 4. So everything that's above this dashed line here would correspond to a reinforcement that's stronger than the probability of a neutral allele to become fixed in a population of 10,000 individuals. So you can see that, for larger populations, reinforcement seems to be stronger in this, if we interpret it like this. And here, for example, for a small population, reinforcement will maybe only be important if it's working with a 1 allele mechanism. And so to put this together here again, so the invasion rates are relatively small, I would say, and they decrease quickly. And looking at the equations again, we can see that they are decreasing proportional with PE, which means that they are decreasing inversely proportional to the preference, to the strength of the preference. And in most of the cases, we see that the 1 allele mechanism is stronger than the 2 allele mechanism. And this is so in our approximations for small modifiers of small effect show that this is mostly due to a negative contribution of the effect of the modifier on extreme phenotypes to this invasion rate of the modifier. And so to summarize, we have made the first quasi-linkage disequilibrium approximation, and we found simple approximations for the invasion rates of 1 and 2 allele modifiers, which might provide some kind of estimation of when reinforcement is important. And we have also found simple analytical quantifications of reinforcement as a result of 1 and 2 allele mechanisms with the same model. And I haven't shown all of this, but our conclusions are that reinforcement can complete speciation, and in particular we find that modifiers of complete speciation always have the highest invasion rates, and we find that reinforcement is strongest in intermediate stages of divergence, and the range of importance is hard to predict because it's very much dependent on, for example, the population size and on the parameters like the preference function, and we also find that reinforcement can be driven both by natural and sexual selection, or by both, or just by one at the same time. And in most cases, we find that reinforcement is actually really much stronger in a 1 allele mechanism than in a 2 allele mechanism. And that's the end of my talk, and I thank you for your attention, and I thank my collaborators and their groups for working with me, and Joachim for his supervision of my PhD.
Thank you, Claudia. Could I ask if there are any questions, since you're requested over there?
Somehow I felt that you reached the opposite conclusion to Maria.
I think so. The difference in Maria's models is that it's more like assortative mating based, so there's a female preference, but it increases the mating with your own type, and I have this preference model where you really have a female preference for a male trait. And no, we don't necessarily have sexual selection in our model. So it also works if we just, have only natural, like viability selection on intermediate phenotypes.
Okay, so if it is correct, we calculated the selection coefficient with it's an alternative delaying time that was quite different from the rest of it. Or am I mistaken? Am I misunderstood? I was just referring to range results showing that a sort of intermediate level of a sort of maybe actually selected one. And so speciation has stopped halfway somehow. You relate that in your results?
I think I didn't totally acoustically understand your question, I'm sorry.
So my question is, if you look at a gradual reinforcement rather than the invasion of a new type that would somehow go away to complete speciation, or maybe I misunderstood your analysis, I'm not sure.
So I think the main point is to start at a point where we already have a high preference and then add a little bit to it.
So it wasn't that was my real answer. So,
Yeah, perhaps I can ask a question about the costs of this modifier and the preference in general. So it seems to me that if you have a low density of one of these mates, it would be rather costly to have a preference for that mate. Is that something you have considered or might build into the model in the future?
So not yet and not at the moment. But yeah.
Are there other questions? Okay, if not, then let's thank Claudia again.